So welcome back to Unit 2. What I'd like to do in this lecture is to continue our discussion of traditional MOSFET theory. In the last lecture, we did it very simply. We developed simple expressions for the linear regime current and for the saturation regime current. What I'd like to do now is to show you a simple theory where we can go smoothly from the linear to the saturation region, smoothly connect the two regions and go in between the two. This is a classic analysis of a MOSFET. Dates back to the 1960s. Doesn't describe current day MOSFETs very well, but it's worth seeing, and it's something that's discussed in every textbook on MOSFETs, so we should see it. All right, here's our square law MOSFET. We've discussed the linear regime where the device operates like a voltage-controlled resistor. We've discussed the saturated regime where the device operates as a gate voltage-controlled current source. And we discussed one type of transistor that we called a square law transistor. These tend to be long channel length transistors, where the current is in the saturation regime is proportional to the square of the gate voltage minus the threshold voltage. Okay, so what we want to do is to see if we can derive these IV characteristics, not just the two red regions, but everything in between. All right, so how do we formulate them? We remember that current is charge times velocity. It's also proportional to the width. Now we're thinking of velocity as due to an electric field, which is sweeping the electrons along the channel. The velocity is minus mobility times electric field. Minus because this is an N-channel transistor. The charge carriers are negatively charged electrons. And you may remember that electric field is minus the gradient of the electrostatic potential, so I can also write the velocity as proportional to dV dx. All right, I put that together, and then I have an expression for the drain voltage in terms of the charge, the mobility, and the gradient of the electrostatic potential. I can separate variables. Before I do that, I'll just point out that we're only including the drift current here. You might worry about, well, what about the diffusion current? We could do the analysis. It's a little more involved, but if I replace the electric field by the gradient of the quasi-Fermi level, then both drift and diffusion are included. But, we'll save that for another time. All right, so we have an expression for the drain current. We can separate variables. We have the current is constant along the channel. So we have I dx. And then we have a function of voltage on the right-hand side. We can integrate both sides. We'll integrate the left-hand side from 0 to L. So that's bringing in a 1 over L here. And we're integrating voltage from the source voltage, which is 0, to the drain voltage, which is Vd. So now we've got an expression. All we need to do is to specify charge as a function of voltage in the channel. All right, now before I do that, let's go to a simpler device. This is a one-dimensional MOS capacitor. No variation in the X direction. If I apply a gate voltage, things will vary in the Y direction, normal to the gate. Okay. Now, if the voltage is less than the threshold voltage, there is no charge. That's our approximation. In reality, there's a small charge. We'll talk about subthreshold charge later in the course, but for now, we'll assume that below threshold, there's no charge. Above threshold, we've written the charge very simply. It's negative because there are electrons. It's proportional to capacitance times voltage, as it is for any capacitor. But this is only the charge due to the mobile electrons. And we only have charge due to mobile electrons when the gate voltage is bigger than the threshold voltage. So we get a nice, simple expression for the mobile electron charge as a function of gate to source voltage. Okay, now we have a more complicated device. We have a two-dimensional device. We not only have electric fields in the normal direction, in the Y direction. When we apply a drain to source voltage, we have electric fields in the lateral direction. So this is actually a more complicated problem, but we're going to make it simple. The way we'll make it simple is that we will try to use this simple 1D result for the MOS capacitor and just extend it appropriately. To do that, we need to make an approximation, and we'll make an approximation that is known as the gradual channel approximation. And the idea behind that approximation is that the electric field in the direction normal to the channel is very large compared to the electric field along the channel. So you can see that this is going to tend to be valid in long channel devices when the channel isn't too short. Okay. Now, if I make that approximation, we could argue that the results should be very much like they were in the one-dimensional MOS capacitor place. There's only one thing I have to worry about, that as I move down the channel, the voltage underneath the gate is changing. It's increasing from 0 to the voltage at the drain, and I have to take that into account. So at each point, I'll use a one-dimensional solution, but there'll be a different voltage in the silicon underneath. So we can simply do that by extending, instead of just VG minus VT, we now have to subtract the voltage in the silicon, because if there's a positive voltage in the silicon, which there will be near the drain, that's going to work against the positive voltage on the gate and will give me less charge in the channel. So we have a simple expression now that we've extended to treat the MOSFET. We can use that to evaluate the IV characteristics of the MOSFET. This expression assumes the gradual channel approximation. So we now have a channel where the inversion layer charge, the amount of charge varies. There's more of it at the source where the voltage is low, and there's less of it at the drain where the voltage is high. All right, back to our IV relation. We now know how to specify Q. We put our expression for Q in there. We do the integral. It's an easy integral to do. And here's the result. So we have an expression for the IV characteristic of the MOSFET, and it wasn't too hard to get. Now, this region of operation is, which we'll plot in a minute, is known as the triode region of operation. Why is it called triode? Because years ago, in the 1960s, when people were first figuring this out, vacuum tubes were still the dominant electronic device. When people saw these IV characteristics from these new devices called transistors, they said, oh, that looks like the IV characteristic of a vacuum tube triode. And that's why it's called the triode region. All right, let's plot this characteristic that we just derived. If we sweep VGS, if we sweep the drain voltage up to VGS minus VT, we'll get a curve that looks like this. And you can convince yourself that once the drain voltage hits VGS minus VT, the slope of this curve becomes 0. As the drain voltage gets bigger and bigger, the current rolls off, and at this critical voltage, VG minus VT, we reach a maximum. Okay. Now the question is, what do we do? Do we continue to use that expression at the maximum value of the current? Or if we do it, the current would turn around and go down. That doesn't seem quite right. It seems kind of unusual. In fact, that's not right. So what's going on here? Well, what's going on in this region is we would say that we are beyond pinch-off. So what is pinch-off? Well, if I look at the charge at the channel, it's minus Cox, VG minus VT, minus the voltage in the silicon at the drain end. So this is the charge at the drain end of the channel. Now, when I put that voltage equal to VGS minus VT, you can see that I'm going to get 0 charge. So if I have 0 charge, how am I going to get finite current? Well, I don't mean exactly 0 charge. There's going to be a small charge there. That small charge has to carry the current. What's really happening here is that at this point, the gradual channel approximation upon which this expression is based has broken down. And I have to stop. I can't use it any further. I have to figure out what is the physically reasonable thing to do. So our gradual channel approximation has failed, but current is still going to flow. And we can see why current still flows if we look at an energy band diagram. So this is an energy band diagram from a numerical simulation for a MOSFET. Here's the source, here's the channel, here's the drain. We're increasing the drain to source voltage, so we're pulling the voltage in the drain down. If I look at a very large drain voltage, you look at the conduction band there, you'll see that there's a point there where there's a change in the slope of the conduction band profile. The slope is proportional to the electric field. So it means in the region beyond that point, the electric field is very high. Well, that point is the pinch-off point. At that point, we're at the end of the channel. There's a small amount of mobile charge, but that mobile charge is just going to drop down in potential energy and go out the drain. Or we can think of the large electric field as sweeping it very rapidly out of that small part of the channel into the drain and out the contact. So there's no reason that the current would stop flowing. In fact, it's easier for current to flow once it hits that high field regime. If you look at the velocity as we increase the electric field, increase the drain voltage, you can see that the velocity in that region is very, very high. So electrons that hit that pinch-off region, they don't stop flowing, they just get swept rapidly out into the drain and out of the device. So that's what the physics of pinch-off is all about. You know, in our textbook model, we say that pinch-off means that the mobile charge is zero, but we don't really mean that. We mean the mobile charge is very small, the electric field is very high. That very high electric field takes that very small mobile charge and keeps the current constant. So this is what the IV characteristics should look like then. We have the characteristics in the triode region. We hit the maximum of the current. Now our gradual channel approximation breaks down, but the current just continues to flow, and it continues to flow at that maximum value. That's the saturated current. All right, so we've derived the complete IV characteristics of this square law device. When the drain to source voltage is low enough that pinch-off does not occur, we have this expression for the triode regime. When the drain to source voltage exceeds this critical pinch-off voltage, the device is pinched off, and we have our square law character. We have our saturated current, independent of drain voltage now. If I look a little more carefully at the linear regime, where is the linear regime? I've mentioned triode regime. I haven't said anything about linear regime. In the previous lecture, we derived the IV characteristics in the linear regime. Well, linear regime just means very small drain to source voltage. If I look at this expression for the triode regime, and if I make the drain to source voltage small, let's say 1/10 of a volt between the drain and the source, then VDS squared is 1/100 of a volt. All right, so it gets small enough it can be ignored. When it can be ignored, what I'm left with is this simple linear region expression, which is exactly the expression that we derived in the previous lecture. So this result is consistent with the previous results. It just gives us the entire IV characteristic. Now, it's also interesting to look at the electric field in the channel. Let's do it under small drain to source voltage first. We have an expression for the linear region current. We know that current is charge times velocity. We know that the charge is Cox Vg minus Vt. The velocity is minus mobility times electric field. We can put these together and solve for the electric field at the source. And we find that the electric field, as expected, is in the negative direction. It's just the drain to source voltage divided by the channel length. That's what we assumed in the previous lecture. What happens under large drain to source voltage? Well, we have an expression for the current now, our square law expression. We know that current is always proportional to charge times velocity. The velocity, the charge at the beginning of the channel, where the voltage in the channel is 0, is still Cox Vg minus Vt. The velocity is minus mobility times the electric field at the channel, at the source end of the channel. Put these expressions together, and we get an expression for the electric field at the beginning of the channel. Now, the voltage across the channel is Vg minus Vt at the drain end, where it's pinched off, and it's 0 at the source end. So you might think that the electric field is just Vg minus Vt divided by length of the channel. That's not true in this case, because under high voltages, the electric field is nonlinear. It's actually less at the source end of the channel. You know, when we do this math, we find that there's a factor of 2 on the bottom. It's half of the average value in the channel. Now, that's the factor of 2 that I had to magically put in the previous lecture. I just pulled it out of the air. And here it comes out of the analysis, so we get it for free. So we could look at the electric field anywhere, at any position in the channel, using a technique like this. All right, so that's the derivation of the IV characteristic of a square law MOSFET. Just to summarize, for low drain to source voltage, we have what we call the triode regime. For very low drain to source voltage, this simplifies even further into the linear regime current. For larger drain to source voltages beyond this critical voltage called the pinch-off voltage, Vg minus Vt, the current saturates, and it saturates at a value that's proportional to the square of gate voltage minus threshold voltage. So that's our IB characteristic. Now, that's a classic derivation. If you make the channel lengths long enough, you'll still see MOSFETs behaving that way. But modern MOSFETs tend to have short channel lengths and do not behave as square law devices. They're linear devices. The current goes as Vg minus Vt to the first power. But this example is an example of how you can derive an IB characteristic that goes smoothly across the whole range of drain voltages. Now, we could do the same thing for the velocity saturation model that we discussed in the previous lecture. That would be more relevant to modern transistors. That's a little more complicated even than this analysis that we went through here. Now, it turns out that there is an easier way to do this. We can take the linear regime current that we derived in the previous lecture. We can take the saturation current in the velocity saturation model that we derived in the previous lecture. And we can very simply and smoothly connect those so that we can go smoothly from small drain to source voltage to large drain to source voltage. And that's a model that is really worth seeing, and we're going to be talking about it a lot in the subsequent units of this course. That's the topic for discussion in the next lecture.